On the last lecture, I formulated a theorem which said the following, that for any system of linear equations, solution set has the form. So essentially, our x is p plus c1 beta 1 plus c2 beta 2 plus and so on plus ck beta k on c1, c2, ck are real numbers. P is a particular solution of system of linear equations, and beta 1, beta 2 number of beta 1, beta k, sorry, equals the number of free variables. After Gauss-Jordan reduction or Gaussian elimination, whatever. So now let me give, so I explained already that a homogeneous system of linear equations is a system of linear equations with zero right-hand side, right? So, okay, let me give a little bit more formal definition. A linear equation is homogeneous if it has a zero right-hand side or constant. Just like that. Okay. And homogeneous system of linear equations consists of homogeneous equations. Okay, so we already considered it and even considered applications. Now, let me formulate the lemma. For any homogeneous system of linear equations, or any equations, there exist there exist. Pay attention. Later, I will use this sign, which means exist. So it's so-called quantar, and you will encounter it later if you will take, for example, course of mathematical analysis or practically any other course with proofs. So there, this notation is used. So there exist vectors beta 1, beta k, such that the solution set of the system is C1 beta 1 plus and so on plus Ck beta k, where C1, Ck belong to the set of real numbers, where k is the number of free variables in an echelon form of the system. Or I will use row echelon form of the system of linear equations. Okay, so essentially proof is simple. So, and it will be like that. So let us apply let's apply Gaussian elimination to get to the row echelon form. So there can be some zero rows, right, in the row echelon form, and we ignore them. So here, because equation 0 equals to 0 is trivial, right? Ignore. Okay. What is interesting that we cannot have contradictory equations, right? Because system is homogeneous. So we started from the, pay attention, homogeneous system of linear equations, right? So we know that homogeneous system is consistent always because it always has so-called trivial solution. All unknowns are equal to 0, right? Okay. So okay, and we will use so-called induction proof to verify that each leading variable, so or variable with the leading one, remember we have leading variables and free variables, right? So so each leading variable can be expressed in terms of free variables. And this will finish the proof because we can use free variables as parameters, and betas are the vectors of coefficients of those free variables. Okay, so what does it mean, induction proof? So we use use a base case. So first use just okay. Check the statement for a simple case. Induction on some parameter. Case usually parameter n. Parameter n equals to 0 or n equals to 1, etc., etc. Okay, suppose statement works for n equal to k. This is called induction hypothesis. Three, prove that it will work for n equal to k plus 1. End of the proof. Why it is end of the proof? Because have a look. We have some base case to start from, right? N equal to 0 or n equal to 1 or just some other simple case where we can just check that our statement is working, right? So then we essentially are saying that let us suppose that it works for n equal to k. And then we use algebra and logic and use these hypotheses to prove that then it will work for k plus 1. Why it's end of the proof? Because we can start from the base case, n equal to 1, for example, or n equal to 0. And then, because we have proven that if for n equal to k it works, so then it will work for k plus 1. So then we can make one step further. So from n equal to 1, we already know that it will work for n equal to 2. Now we use n equal to 2 as a base step, and now we can make another step to n equal to 3, and so on to wherever we need, essentially. Is it clear or not, the approach, the induction approach to proofs? Because we will use it in many cases. Okay. Any questions with induction? In linear algebra, this is one of the main approaches to proofs. Okay. So if you feel that you do not understand it, please come to the office hours. We will do some examples. Okay. Induction. First, base case. Consider the bottommost non-trivial equation. meaning not an equation like 0 equals to 0, okay? So some equation which has non-zero coefficients in it, right? Okay, so the bottommost equation, as we know, will have the following form. X, if you will write it in components, right? So remember, I told you that in row echelon form, so I asked you to get to the situation when the leading coefficient is equal to 1, right? So it means that we have the following equation. Really, yeah, okay, I will keep it like that, equals to 0, right? So because why? Because you will have something like that. So in the row echelon form. So and this is bottommost. So and some coefficients here, right? So then this coefficient is the coefficient in front of this is LM column. So corresponding to some unknown XLM, right? And then here you have the first coefficient, then the next one, and this is the last coefficient, right? Because it's homogeneous system of linear equations, right-hand side is equal to 0, right? So this is what you will get. So it means that immediately we can write this is mth row. So we expressed a leading variable through free variables. Okay, we see that it works for the bottom row, right? Clear or not?
Clear.
Okay, the only problem which we can have here, if all the coefficients here are zeros, but this is really not a problem. It just means that XLM is exactly equal to 0, right? This will be the equation. So then we just use the next row, the first row where we have free variables, right? Okay. For the induction step, so induction hypothesis. Hypothesis. Assume it holds for t bottommost rows. So it means that for the first t rows from the bottom, it works, right? Let us suppose. So now we need to prove that it will work for it works for t plus 1 bottom most. Okay. How can we do this? It's very easy. So essentially, if it works for the first t rows, right? So it means that XLM equals to minus AM LM plus 1 XLM plus 1 minus minus
Hey, Professor.
yes, go ahead.
Is that T bottommost rows starting from the bottom going up T?
Yes, yes.
Okay. Just trying to make
But
sure it was going up.
starting from here, essentially, this is the bottommost row, right?
Yeah.
Non-trivial. Of course, I'm looking only for non-trivial. Okay, bottommost non-trivial rows. But because row echelon form would give you that all 0 rows will be here, right? So it will be below non-zero rows, right? So by the algorithm, right, of Gaussian elimination. So it means that all rows above will be already non-zero rows, right?
Right.
So as I said, as a base row, I started the first non-trivial, which means non-zero row, right? From the bottom. Okay, is it clear or not?
So it's we're gonna go up. We're gonna assume it holds for T rows above the lowest most non-trivial row.
Yeah, you see, this is exactly how I have shown this, right?
Okay.
So let us suppose that it works for T rows from the bottom, right? Non-trivial rows from the bottom, okay? So then what does it mean? It means that I will have some, okay, LM, if it was mth row, right? Then it can be, so essentially for the first rows, right? For the first, for the first rows here and here T rows. So I can express my leading variables through free variables, okay? So this is the statement, right? I can do exactly this. But then, because the next row, T plus 1th, so T plus 1th row non-zero, non-trivial row from the bottom. If I consider t plus 1's non-trivial row from the bottom, I will be able as well to express the leading variable through previous unknowns, right? So pay attention. When I considered the bottommost row here, so I don't have any leading variables to the right from this leading variable, right? So here I expressed my corresponding leading variable through the free variables, right? Is it clear or not? Because here we don't have any leading variables, right? So here we have only free variables because it's the bottommost row. So let me remind you that free variables are variables corresponding to, okay, leading variables are variables corresponding to leading ones. Here in the bottommost row, I can have only one leading one, right? I cannot have two, obviously. So correspondingly, all other variables to the right will be free variables. So this is exactly what I've done here. I expressed my leading variable through free variables. Now, I said that let us suppose that I can do this for the first t rows. Pay attention, t rows. Next, if I will consider t plus 1th row from the bottom, so then I will have some leading variable, right? Let me call this okay, L m minus t plus 1, right? And I will be able to express it through, pay attention, all previous variables. Or previous right? Some of them will be leading variables. Some of them will correspond to the free variables. It doesn't matter. Is it clear or not?
It makes sense.
Okay, but the thing is that these are all variables which are, for example, if this is leading one, which were, these are the previous variables which I already considered. But for them, I have induction hypothesis saying that I was able to express them, pay attention, through the free variables. Then I will just substitute previously expressed leading variables through free variables, right? Because according to induction hypothesis, this one, so we said that we can express the leading variables through free variables, right? Okay, next equation, which is one step upper, right? So for example, here, it contains only previously considered unknowns. Okay, instead of leading unknowns, I substitute the previous expressions of leading unknowns through free variables. And then I'm getting that I can again express my leading variable through free variables. End of the proof. Clear or not?
I get the concept, but I kind of,
Excuse me, could you please repeat that?
so I'm solid on it and like the concept, but like I'm a little shaky when it comes to like showing it without words. Is it possible to with words mathematically express proof?
I mean, it's inevitable to use words in the proof. So, I mean, it's just in many cases it's faster. So, because here you can see clear logic, right? I hope.
Yeah.
Yeah. So, if you can express this logic through words, and it's clear, then it's enough. So, I mean. Just if you will have a look at the proof at the book, it's more or less in the same style. So once again, you cannot avoid words in the proof because you're explaining your logic. Okay?
Professor, could you give examples of how to use this?
Yeah, we really did it before. So essentially, okay, let me, yeah.
I mean, I think I feel like I know what it is that we're
No
trying
problem.
to do.
Yeah, here it is. Here it is. Okay, I already have written the equation in the row echelon form. Okay, is it clear or not? System of linear equations, homogeneous system of linear equations in the row echelon form. Okay, is it clear or not?
It's clear.
Okay, could you tell me the coefficients matrix?
Would it be 1, 1, 2, 1, 1? And
Okay.
then you don't have to put the 0, so you can close the matrix, right?
Yeah. Okay. Let me write zeros.
Oh, I mean at the answer signs.
Mm-hmm.
And then it's
Yeah.
another...
Because yeah, to the right, in the right hand side, this will stay zeros whatever row operations we do, right? So this is why we omit them. Okay. First, next, sorry, 0, 1.
And then you have 1, 1, -1.
Okay, and here
3 0, then 2 1s.
Okay, perfect. Okay, so for this, for the bottommost row, right? I have the following: x4, pay attention, leading variable, right? Plus x5 equals to 0, right? So, oh, sorry, x5. So correspondingly, I can express x4 through x5, right? Clear or not?
Clear.
Okay, now, so it was this line. In this line, so how can I express this line? This line I can express, I can write as x3, sorry, x3 plus sorry, x2. We start from x2. x2 plus x3 plus x4 minus x5, right, equals to 0. So obviously, I can always express my current leading variable, right, this one, through all other previous variables, right? So minus
Can I ask
x.
a question? Maybe it's a little too soon. But we said that x4 is equal to negative x5. So would we plug that into the
Not yet,
equation?
not yet. You see, so this is exactly what I said in the proof. So first, I use the statement that I can express my leading variable through all other variables which are present in the line, right, in the row. But pay attention that these variables are either free variables, right, or leading variables which we considered before, right? Clear or not?
Yeah.
So now I'm doing exactly what I just said. Now, instead of all leading variables here, I substitute their previous expressions through free variables, right?
Okay, so you do put, for
Yes.
x4, you put in negative x5, and you can express it in less than 3 variables now.
Yes. What is important, I don't care how many variables. What I care about is that I expressed my leading variable through free variables. This was the thing which I was trying to prove, that I can express. So here it is, the formulation of the theorem. Here I can express through free variables, right? So these columns correspond to free variables, right? Clear or not?
Yes.
Okay, let us continue. So now let us consider the last equation. It will be x1 plus x2 plus 2x3, right? Plus x4 plus x5 equals to 0, right? So here I can express my x1 through all variables which are to the right from it, right? Now, exactly as before, I will just substitute instead of x4, instead of leading variables x4 and x2, I will substitute previous expressions, right? So this is instead of x2. Instead of x4, negative x5, right? Sorry. Just like that. That's it. So I again expressed my leading variable through free variables.
Okay, so I understand how to do this and where it comes from, but is there a specific reason why we do this?
Exactly. So let us now write the solution. So this is how it will look like. Okay, x1 equals to x3 minus x3, right? Minus 2x5, right? Okay, x2. Here it is, x2 minus x3 plus 2x5. x3 is a free variable, right? x4, where it was here, equals to negative x5. x5 is a free variable, right? So can take any value. Okay, now let me replace x5 everywhere with beta. And let me replace x3 everywhere with alpha. Okay, now I'm getting the following: x1, x2, x3, x4, x5 equals 2. So alpha -1, -1, 1, 0, 0, plus beta -2, 2, oh yeah, 0, -1, 1. This is my so I represented the solution through the linear combination of two vectors, and number of these vectors is exactly equal to the number of free variables, because these coefficients are nothing else but exactly free variables. Is it clear or not?
Yes.
Okay. Yeah, by the way, what we could do here, so I just followed the proof in your book, but because we already introduced a reduced row echelon form. So in reduced row echelon form, you would get rid, so you would essentially would get rid of other leading variables in your expressions, right? So you would not have these x2 and x4 coefficients, non-zero coefficients here. Because what we do in reduced row echelon form, we eliminate all coefficients on top of leading variables, which exactly correspond to substitution of these leading variables into equations above these leading variables, right? Any questions?
So here the leading variables are x1, x2, and x4, and we're replacing each of those with expressions involving x3 and x5.
Exactly, exactly. Which means we are expressing leading variables through free variables, right?
Yes, that makes sense.
Okay, perfect. Okay, now I can formulate the next lemma, which says the following. For a linear system, and for any particular solution, of it, the general solution or solution set equals particular solution plus H, where H is a solution set of corresponding homogeneous system of linear equations. Okay, so pay attention that H, so if I start from any system of linear equations, right? So it's not necessarily has the right-hand side. Clear? I mean, not necessarily has zero right-hand side, sorry. So it means that what I do first, I first could say that, okay, let me consider the simpler case of homogeneous system of linear equations, right? So I just zero out the right-hand side. Then I can use the previous lemma, which says that the solution set of the homogeneous system of linear equations can be expressed as a linear combination of some vectors, right? A number of these vectors is exactly equal to the number of free variables, right? Pay attention that regardless of whether your system is homogeneous or not, the number of the free variables will be the same, right? Because number of free variables depends only on the coefficients matrix, not on the right-hand sides, right? So it, regardless of the right-hand sides, you will be, when you will be performing Gauss-Jordan reduction, for example, so you will be working only with the coefficients matrix. And the right-hand sides, they are trailing, right? So you just have to perform exactly the same elementary row operations on the right-hand sides as you do during Gauss-Jordan reduction on the coefficients matrix. Clear? Okay. So statement is the following, that if I will be able to find any particular solution, which means just any solution of my original linear system, regardless whether it's homogeneous or not, right? So my original linear system, then solution set will be this particular solution plus the solution set of the homogeneous system. Okay, proof. Proof. First, so essentially, idea is that when I'm saying that the solution set equals to that, I need to prove it in both directions. So I need to prove that if I consider some solution in this form, or some vector in this form, if you like, So it will satisfy my linear system. And vice versa. If I have a solution of the linear system, it can be represented in this form. Okay. So what does it mean that vector solve the system? Let us assume, so one direction. Assume S solves the original system of linear equations. Okay. Then S minus P, where P is a particular solution, solves homogeneous system of linear equations. Have a look. Let us substitute this into our system of linear equations. So we are getting AI1. So if I'm talking about ith row, AI1, S1 minus P1. So let me remind you that S minus P will be the following vector: S1 minus P1, S2 minus P2, and so on, Sn minus Pn, right? So now I'm substituting it in my ith row.
I'm sorry, I have a question.
Yeah, go ahead.
Yeah, I don't quite understand S minus P. Why did you subtract P?
I'm just saying that P is any particular solution of my system of linear equations. It means some solution, just one. I have just found a vector which satisfies my system of linear equations, one. Okay? I mean, I guessed it, if you like. Okay?
And yeah, and we're and that's the thing that
yeah, it's this is P. P is a particular solution. Particular solution P of it, of the original system of linear equations. Is it clear now or not?
Yeah, it makes sense.
Okay. So how can I write it? It will be this. Okay, if I will open bracket, so I will get this. Right? Any questions here?
Professor, I think you got an X where you should have an S, Xn.
Oh, yeah. Thank you very much. Yeah, so trying to write it too fast. So, but as we know, our S is a solution of our original system of linear equations, right? So it's equal to corresponding right-hand side, right? Right?
Yes.
But P is also a solution of our original system of linear equations, right? So it means that it also equals to corresponding right-hand side. So we are having di minus di, which is equal to 0, right? So I have shown that for all rows, I will get 0, which means that S minus P vectors is a solution of the homogeneous system of linear equations, right? Is it clear or not? Okay, so, but then, according to the previous lemma, I can express it as C1 beta 1 plus C2 beta 2, right? Which is nothing else but solution set. So it corresponds to solution set of the homogeneous system of linear equations. It means that my solution can be expressed as this, right? Clear? Okay. We have proven it in one direction, in the opposite direction. So let us consider vector x in the form, in this form. Then, if we substitute it in the ith row, so we will get the following. So pay attention, this will be nothing else but p1 plus h1. So ai1 2 and let me again redistribute it. IN. Sorry. H of course. Yeah. But because this is a particular solution, right, of my original system of linear equations, this will give me nothing else. This has to be equal to the right-hand side in the ith row, right? While this H, right, H is a solution of the homogeneous system of linear equations. So it means that it has to satisfy homogeneous, corresponding homogeneous equation. So it has to give me 0, right? So altogether, I'm getting di plus 0 di. So I started from the arbitrary vector of this form, and I got that it satisfies my ith row, right? Pay attention that I is arbitrary, right? So I got that if I start from the solution in this form, it will satisfy, I mean, if I start with the vector in this form, it will satisfy my original system of linear equations. So I have proven that all solutions of my original system of linear equation can be represented in this form. Is it clear or not? Any questions?
No, it makes sense to me.
So as a result, I can write the following rule. General solution is particular solution plus solution of the homogeneous equation. Okay? Clear or not?
Does the solution for a homogeneous equation always have to be 0? or could it be something else?
No, no, no. I said that, have a look. Here, this is a solution set of the corresponding homogeneous system of linear equations, which means that depending, if of course you don't have free variables, right?
Right.
Then obviously your homogeneous equation will give you just trivial solution, right?
Right.
So which means that will be only zero. But if you have free variables, right, then correspondingly your solution will be this. So we essentially proving these two lemmas, we have proven the theorem which we formulated in the end of the last lecture, that any solution of the system of linear equations has the following form: some particular solution plus a linear combination of some vectors. A number of these vectors is exactly equal to the number of free variables. If you don't have free in the homogeneous equation or whatever, because homogeneous equation will have the same number of free variables as inhomogeneous one, right? So with the same coefficients matrix, right?
Yes.
So it means that if you don't have free variables, then you will have just particular solution. Obviously, if this system is originally homogeneous and you don't have free variables, the only solution will be zero.
Okay.
But if you have free variables, right, then you have linear combination, right, of some vectors.
Right.
Maybe one vector, right? So essentially, from here, we can immediately formulate the following corollary. Solution set of any system of linear equations is either empty, inconsistent, have one element, unique solution. Or have infinitely many elements. Solutions. So because the only possibility which you can have, so if you have a particular solution, right, if you have vector p, if you have it, at least one solution in the system, right, so it means that there is at least one solution, then at least one element is present there, right, in the solution set. So then, depending whether you have free variables or not, you have either this one element, right, or you have infinitely many elements if you have even one free variable. Clear or not?
Clear.
Or your system can be inconsistent, then there is no even one particular solution, right? So there cannot be situation for the linear system. Pay attention, what is important here, linear system of equations, system of linear equations, sorry. So for system of linear equations, there are only 3 possibilities. System is inconsistent. If system is consistent, then it can have either unique solution or infinitely many solutions. So it cannot have, for example, only 2 solutions or only 3 solutions. Either unique solution or infinitely many if the system is consistent. This is extremely strong statement, and it just follows directly from the form of the solution which we have proven. Okay, now let me give a definition. A square coefficients matrix. So matrix of coefficients for the system of linear equations, which has the same number of columns and rows, meaning that we have the same number of unknowns and equations, right? Because number of columns is equal to number of unknowns, right? Number of rows is equal to number of equations. So a square matrix is non-singular if it is the matrix of coefficients of a homogeneous system with a unique which means trivial, right? Solution. It is singular otherwise. Singular otherwise. Infinitely many solutions. So what is interesting that and this is direct consequence of the theorem which we have proven. Okay, if I will consider the following 2 matrices, so this is singular and this is non-singular. By the way, how you can easily see that this matrix is singular? So if I will multiply the first row by 3 and subtract from the second row, what will happen?
You would get 0.
Yes, exactly. It means that rows are proportional to each other, right? So it means that I have free variable, right? At least one free variable. It means that my homogeneous system has infinitely many solutions, right?
Yeah.
Because this is how you can write it, right? And then you're getting that x1 equals to negative x2 x2 is free variable, right? And I can write it like that. So which means that any alpha belonging to set of real numbers, right? So this is any. It's another quanter which is also used in standard notation for any for math books. Okay, so now the statement is the following: that if you have a singular matrix, then you can have either no solutions or infinitely many. If you have, because I mean, yes, your homogeneous system has infinitely many solutions, but if you consider general system with this coefficients matrix, right? What you can get inconsistent system, right? So for example, here, so I multiply this by 3 and subtract it, right? Okay, let me consider system like that. One, okay. X1 plus 2x2 equals to 1. And 3x1 plus 6x2 equals to, let's say, okay, 3. Then the system is consistent, right? Because I will get here 1, 0 as a result, right? Augmented matrix like that. But if I would have here, I don't know, something like 2, for example, then this would not be 0 and my system would be inconsistent, right? So as a result, I know that if I have a singular matrix, then either my system is inconsistent, I cannot find any particular solution, right? Or my system has infinitely many solutions. Why? Because it will be a particular solution plus solution of any solution of the homogeneous system of linear equations, right? With the same coefficients matrix. Well, if my matrix is non-singular, then again, situation is the following: that either, so what can you tell me? What can I have? What situation can I have if my matrix is non-singular?
Professor, can I ask a question?
Yeah, go ahead.
Maybe it's going to backtrack a little bit, but you had the singular matrix 1, 2, 3, 6, and then you changed the solutions in the drawn out variable form.
Here or what? Yeah.
Yeah.
I just,
How is that no longer singular, or is it still singular? And
no. Pay attention. Singular can be only matrix itself.
So it can equal anything?
Yes. So if matrix is singular, so which means that, pay attention, corresponding homogeneous system of linear equations has infinitely many solutions. Okay?
Okay. So when we're looking at this, we're only looking at
the coefficients
square
matrix. The coefficient, yeah, only square matrix, yeah.
And
so,
only for the coefficients, we're not looking at the right-hand side.
Yes. First of all, definition has talking only about square coefficients matrix, right? Pay attention,
Okay.
Coefficients matrix, not augmented matrix, right?
Okay, so I guess my question is, could they equal anything?
Yes, so you see,
equal anything?
Yes, for example, if you will consider this, right? So your your coefficients matrix is still 1, 2, 3, 6, right? But augmented matrix is already this, right? Right?
But the augmented matrix and the coefficients matrix are not the same thing.
Of course, yes, coefficients matrix is only this part gives you coefficients matrix.
Okay, that's just the clarification that I wanted.
Matrix also takes into account the right hand side. Yeah. I mean, I tried to give it this definition, but probably I was not completely clear before. But it's good that you are asking this question because it's very important.
No, it's okay. I've just never learned matrices before. I just kind of watched a Khan Academy.
No, but this is where we started. We just started it, so it's completely okay. So that it's not completely, I mean, not obvious. Okay, so now because we know that we can get zeros here, 0 row here, right? Then if we will not get 0 in this position, right? So then we know that we can have inconsistent system, right? Clear or not? We can have it theoretically.
Yes, I see.
While if we have non-singular matrix, what does it mean? It means that there are no free variables, right? Clear? Because if we have free variables, we have infinitely many solutions of the homogeneous system, right? But if we don't have free variables, pay attention, it means that if we have square matrix, which is non-singular, we always have a unique solution, always. Because what we will get, there are no free variables, we will get in the end, okay, if it's, this will be our row echelon form. And it doesn't matter what we have in the right-hand side, because it will be just this variable is equal to that, then we can perform backward substitution is equal to that, and so on and so on. Or if you like, if we have reduced row echelon form, we will get a matrix with just ones on the diagonal and corresponding values of the x1, x2, and so on till xn in the right-hand side. Clear or not? Because we don't have free variables, right? So we cannot have inconsistent system in this case. Pay attention that singular and non-singular are defined only for square coefficients matrices. Okay, thank you. I will stop here. Sorry for delay.